Okay, so here we go. Let me clear. Okay, now, learning objective for today, we're gonna go ahead and do complex solutions of polynomial equations. So complex, it's gonna come back, guys, where we have our beautiful complex numbers. So we have two different types of solutions. We have a real solution and we're gonna have a non-real solution, right? We're gonna have a complex solution here in this case. Now, we have still polynomial equations. We have two variable equations that have monomials or a sum over differences of monomials. And we're gonna go ahead and ask ourselves, how do we solve these beautiful polynomial equations that have complex solutions? So not only does it have non-real solutions, it's also going to have something else that we're gonna go ahead and define as well here, okay? Now, something that I wanna go over, guys, is very quickly is the fundamental theorem of algebra. And this theorem is stating that if we have a polynomial with a degree greater than 1 and has all the terms right there, we're going to go ahead and have numbers or values that we're going to go ahead and consider them as solutions, or basically zeros, and are going to be included with either a complex number or a non-complex number, which we consider a real solution. Now, this means that for every function that we have, again, it has a degree greater than 1, we have exactly n zeros. So that many number of solutions. For example, let's go ahead and say we have x squared plus 4x plus 4. If we were to graph this beautiful equation, or we were to find how many solutions or how many zeros it would have, notice here that its degree is to the power of 2. Therefore, we're going to have that many zeros. So how many zeros are we going to have here? 2. So this one is going to have 2 zeros. Okay, let's go ahead and say that we have x to the power of 3 plus x to the power of 2 plus x plus 1. In this case, what is our highest degree? 3. Therefore, how many zeros are we going to have? 3. So we're going to have 3 zeros. So that's what we're going to go ahead and review today. The amount of number or our highest degree in our polynomial that we have included here is what the number of zeros we're going to go ahead and have in this case, including what we're going to go ahead and define right now is multiplicity. So how many times it repeats that value itself, okay? All right. Now, very quickly, let me go ahead and define our beautiful complex numbers. We have our beautiful real and non-real. Goodness gracious, there you go. Our complex values, remember that we're going to go ahead and write them as our real plus our non-imaginary numbers. So real numbers include 17, -5, pi, everything that's included in the real number component. And our imaginary numbers are going to be included as well. So together, whenever we combine them two, are going to be considered our complex numbers. They're coming back again, okay? Ready? No? Okay. I'll let you guys copy this down on your notes. Let me go ahead and pause this. All right, so here we go. First example for today. Go ahead and copy this one down. Find the zeros of the polynomial function. We have p of x equals x to the power of 3 plus 7x to the power of 2. So there's different ways to solve for this. We're going to go ahead and first look at our beautiful function. And we're going to go ahead and look at everything that we have here. So everybody has this? Okay. So we have p of x equals x to the power of 3 plus 7x to the power of 2. Now, yes, we can go ahead and look at the beautiful roots that we might have here, possible roots. However, there's another method for us to solve for it here. What do we see that the two terms that are present here have in common with each other? X and what else? X squared. So let's go ahead and factor that out. So we are going to make this equal to 0. We have x to the power of 2. We're going to go ahead and factor it out. And we're left with x to the power of 1 and 7 on the other side. Now, this entire polynomial is equal to 0, which means that this term is going to be equal to 0, and this term right here, or this beautiful factor, is going to be equal to 0. So we have x to the power of 2 equals 0, and we have x plus 7 equals 0. Now, in this case, I know that x squared, inverse of squaring, is going to be 2 square root. Therefore, x has to equal 0. And over here, we subtract 7. So therefore, x equals -7. However, in order for us to state that x squared equals 0, we know that 0 times what is going to equal 0? Any number, but in this case, it's going to be, again, 0. So we have to include the second 0 in this case. Why is that? Well, our algebra, our fundamental theorem of algebra states that our highest power tells us how many zeros do we have. So in this case, how many zeros do we have in here? 3. So therefore, we need to have 3 zeros. So this will be 0, 0, and -7. So the way that we're going to go ahead and write it is x equals 0. We know that we have 2 of them, so we're going to go ahead and write multiplicity of 2 and -7. Multiplicity of 2. All right. Now, let me go ahead and show you guys really quickly. Everybody has this? Okay, let me go ahead and clear. So this is what we had. We had multiplicity. Our solution was x equals 0, 0, and -2. Multiplicity means that if a 0 of f of x, or p of x in this case, is a root where f of x equals 0, is the number of times related factor that occurs when it's being factorized, or it's factorization. So in this case, we have x equals 0, 0, and -7. We're going to go ahead and write it as 0. We know that it repeats twice, so we're going to go ahead and write it as a multiplicity of 2 and -7. Okay, so instead of writing our solution twice, we're just going to write how many times it repeats itself. Okay, all right. Go ahead and write this one down. Find the zeros of the polynomial function. This time we have f of x equals x to the power of 3 minus 64. We look at each term. Okay, this one doesn't have, this one has x to the power of 3. This one doesn't have an x value, but I noticed that 64 can be written differently. And x can be and has power of 3. So what I noticed here is that because 64 is written differently, I can go ahead and rewrite it as f of x equals x to the power of 3 minus 64. Can we write it to another term or another number where it's the power of 3? In this case, it would be 4. So what we have here is what we call our differences of cubes. So this is our beautiful identity that we've already covered, or if you guys recall. Let me go ahead and bring this one back. For some reason, I copied the wrong one, guys. No, this is our addition of cubes. There you go, differences of cubes. Here it is. There you go. Differences of cubes. There you go. It's a to the power of 3 minus b to the power of 3 equals a minus b inside parentheses. And we have a squared plus ab plus b squared. So from here, we can go ahead and identify which one is our a and our b. So we can go ahead and factor everything that we need to factorize. Okay. So let's go ahead and see. We have a, in this case, would be x, and our b would be 4. So the way that we're going to go ahead and factor this out would be x minus 4. And we have a squared, which is x squared, plus x times 4, so 4x. And go ahead and bring the tool this way. X And b squared, b is 4, so I need to multiply that by itself or square it. And we have x squared plus 4x plus 16. All right, now we need to make this equal to 0 since we have to find all the zeros. How many zeros are we going to have in this case? 3. Since our highest power is 3, we have 3 zeros. Okay, so can we find 1 already? Yes, let's go ahead and make that equal to 0. X minus 4 equals 0. X at 4 on both sides. We have x equals 4. Okay, so we found 1 0. We need to find the other 2. So here is our beautiful quadrilateral that's left. So we have x squared plus 4x plus 16. Now we can go ahead and look up for a number that multiplies to 16. And whenever we add it together, it gives us 4. Do you think we're going to find a number? Not really. Something that multiplies 16 adds 4. So let's go ahead and use our beautiful quadratic formula. So A equals B equals C equals, what's our beautiful A? 1, our B is 4, and our C is 16. So let's go ahead and use that quadratic formula. X equals negative B. Let me go ahead and remind you guys. X equals negative B plus or minus square root of B squared minus 4AC all over 2A. So negative B, so negative 4 plus or minus square root of 4 squared minus 4 times A. C is 16 all over 2 times 1. All right. So we have negative 4 plus or minus square root of 4 squared is minus 4 times 1 times 16. 4 times 1 is 4. 4 times 16. 64 over 2. Let's continue with the inside of our beautiful square root. We have negative 4 plus or minus. Can you guys see it back there? Yeah, okay. Square root of, what is 16 minus 64? Negative 48 over 2. What are we going to have here? Our beautiful imaginary number is the square root of a negative number. So let's go ahead and bring it out. Negative 4 plus or minus, I can't see on my side. Square root of negative 1. And let's go ahead and simplify or rationalize 48. This is, let's see, let's go ahead and factor out 16 out of it. Can we factor out 16? We can factor out 16. We can factor out 4. It should give me, no, 4. 16 times 3, right? Square root of, yeah, 16 times 3. 16 square roots of 3 all over 2 equals, let me go ahead and bring it this way. I ran out of space, guys. Bring it up here. Continue to do our beautiful quadratic formula. Let's see, x equals negative 4 plus or minus square root of negative 1 would give me I. Square root of 16 gives me 4. And square root of 3 would give me 3. So I have 4i square roots of 3 all over 2. Yeah, because 16 times 3, 3 times 6 gives me 8. Put the 1 on top. 3 times 1 gives me 3 plus 1 is 4. Okay. All right. So from here, we can go ahead and reduce. We have negative 4 divided by 2 and plus or minus 4i square roots of 3 divided by 2. We now have negative 2 plus or minus 2i square roots of 3. So therefore, x equals negative 2 positive or plus 2 2i square roots of 3, and x equals -2 minus 2i square roots of 3. So there are our last 2 zeros. We have 1 0 right here, 2 zeros, and 3 zeros. So we have our 3 zeros that we wanted, we needed there in this case. Okay. Ready for one more? You're like, no. Okay. Ready, ready. Number 3, example number 3. All right, so first things first, we need to make our beautiful equation equal to 0. All right, so we need to know when p of x equals 0. Now, before solving it, how many zeros am I going to have?
4.
The highest root or the highest power is going to give me for the number amount of zeros that I have. So in this case, I have 4 zeros. Okay, I'm going to go ahead and put it this way. So I'm going to go ahead and do it differently this time. Instead of looking for a root, I'm going to go ahead and look at all my terms that I have here. And I'm going to go ahead and look at what I have. Do I have this one? Skip this one. Actually, I'm going to go ahead and do it the root method in this case. So I'm going to go ahead and look at my coefficient for my leading term and my beautiful constants. So in this case, m over n, how many roots do I have? Or what are my possible roots? I have -8 and 1, so -8 over 1, so it'd be plus or minus 1, 2, 3, 4, 5, 6, 7, and 8 in this case. All right. Which one do you guys want to try first?
2.
2? Are you sure?
No. 4.
4? Are you sure?
No. 1.
Let's try 1. Okay. Either 1 or 2 or 3 or 4 or 5 or 6 or 8 in this case. I'm just kidding. Let's try 1 first. Okay. So if it's positive 1, it is the opposite. Let's see. Positive 1. Let's see. We have our coefficients. It'd be 1, 5, 6, -4, and -8. We have 1. 1 times 1 is 1. Let's see. This would be 6.
Oh, yeah.
Then -8.
No.
-1. Okay, sorry. There you go. Sorry. This would be -1 then. I was going with the other eyes. Okay. Step by step. I'm going too fast. There you go. -1. 1. -1. This would be now 4. This would be now -4. Positive 2. -2. -6. Positive 6. So what do we get here? -2. Is this a root?
No.
No. So let's go ahead and try -1. So therefore, this is positive 1. So let me go ahead and put my sad face. 1, 5, 6, -4, -8. Bring down our beautiful 1. We have 1 and 1 is 1. This gives me 6. 1 times 6 is 6. This gives me 12. This is 12. It gives me 8. This is 8. It gives me my beautiful 0 that I want. Okay, so we found one root, which is -1. What? Positive 1. Its factor is x minus 1. Okay, now what is left over? X to the power of 3. 6x to the power of 2. 12x plus 8. All right. We do the process again. Now, which one do you guys want to pick? It's still 1 and 8. Do you guys want to go for 2?
Yeah.
Positive 2. Let me do it in a different color. So it'd be -2 now this time, right?
No, it's good positive.
Are you sure?
No.
Let's try +2 first. So we have -2 in synthetic division. Okay. So we have 1, 6, 12, and 8. Let's see, we have 2, -2. This would give me +4. This would give me -8. This would give me +4 and -8 as a solution. So therefore, we found our next root. Woo-hoo. All right, so let me go ahead and write it now in green. So I have x -1, x +2. We have left over x squared plus 4x plus 4. And can we now factorize this? Two numbers that give me multiply to 4, add to 4, which we 2, 2. So in this case, we have x -1, x +2, x +2, and x +2. Yay. So how many of the same solutions am I going to have? 3. So let's go ahead and see. X -1 equals 0. X +2 equals 0. I'm only going to write it once because we have it 3 times, but we're going to note it that we have it 3 times. So we have x +1 and x equals -2. Now the way that I'm going to write it is x equals +1, x equals -2, multiplicity of, how many times does it repeat? 3 times. So how many roots or how many zeros do I have?
4.
1, 2, 3, 4. There you go. Not too bad, huh? So we just have to go ahead and look at our methods that we have here. Did I go over grouping already? I did go over grouping already? Yeah, where I grouped everything together. Did I refresh your memories on grouping?
Think so?
Okay, I just want to make sure. Let me go ahead and, everybody has this?
Yes.
Okay. I think this was my grouping. Yeah, this is my grouping example. So I have one more. Do you guys want me to go over this one?
Yes.
Okay, so grouping. Here we go. The last method that we went through. Very similar to the one in our warm-up. So how many zeros are we going to have here?
3.
3. So we have 3 zeros. So let me go ahead and look at every single term. Do I have a greatest common factor to take out?
Yeah, 2.
2. So let's take out that 2. Órale, pa fuera. So we have x to the power of 3. Let's see. We have -6x squared minus 17x. And this would be 102. Yeah, 102 plus 102 equals 0. All right. Let's see. From here, I know whatever this factor would be, if it equals 0, whenever I multiply by 2, it should be 0. So I'm going to go ahead and not drop the 0, but divide my both left side and right side by 2. So I'm only left with x to the power of 3 minus 6x squared minus 17x plus 102 equals 0. So I'm only interested when this polynomial is equal to 0.
Now we use the m over n.
You can, but let's go ahead and group it. Let's see. Group my first term. I'm going to go ahead and write this over here. Group my last 2 terms. So my first 2 terms, what do they have in common? X to the power of 2. So I'm left with x minus 6. What do my last 2 terms have in common? -17. Let's take out that negative. -17. And I'm having x minus 6 equals 0. What can I factor out? X minus 6. So I have x minus 6 factored out. Like not in yellow. And I'm left with x to the power of 2 minus 17 equals 0. Can I find 1 0 already?
Yes.
Yes, let's go ahead and find that 0. X minus 6 equals 0. And over here, let me bring this little term over here, x squared minus 17 equals 0. Now, we can go ahead and use either the quadratic formula or we can use the square root method here. Which method would you prefer?
Wait, what?
Square root method, since we don't have that middle term. By adding 17 on both sides, we're left with x squared equals positive 17. Square root, and we're left with x equals plus or minus square root of 17. And over here, we add 6 on both sides. This goes to 0. We're left with x equals positive 6. So my solution should be at 6, positive square root of 17, and negative square root of 17. How many zeros do I have? 3, and I have 1, 2, and your 3 zeros. There, it's where your y value is 0, where p of x equals 0, or f of x equals 0. So if I were to create a table, for example, and I wanted to say that my x values were 6, square root of 17, and negative square root of 17, my y value would be 0, 0, and 0. Or my f of x would be 0. Or my p of x, whatever, whichever function I have, my y value in that case would be 0. All right.